All right, hey folks, here we are getting started in chapter 10. Initially, I'm going to start off by doing sections 10.1 and 10.2. Before we really get started in this material, I probably should tell you that, I'm going to have a unique perspective on the material in chapters 10 and 11. And that's due to my learning of this material. See, when I was a student in the calc sequence at Ohio State was on quarters, so the calc sequence was 4 quarters long, as opposed to 3 semesters. At Ohio State, this material was the last material covered in Calculus 4. The professor I had for my Calculus 4 class, as well as my TA, I really couldn't understand them. So I just didn't go to class. I thought I would teach myself the material. In the class, we had 2 tests and then a final exam. That was it. Well, I showed up to class to take test 1, and then I showed up to, pick up test 1. Showed up to take test 2, and then to pick up test 2. And this material was covered after test 2, before the final exam. Well, when I finally got around to looking at this material, I decided I better show up the last day of regularly scheduled class to see how much of this material would be on the final, because it wasn't making much sense to me. Only to find out when I was in class that last day that, because I had, I did well on the 2 tests. I had an A on both. That my grade was an A, and I didn't have to take the final. I had earned an A. So it looked like I didn't have to learn this material. I then go and have a good spring break, come back, and the next class I'm in, the next math class, the math professor starts off the first day saying, let's take 10 minutes to review power series. We won't learn about power series until chapter 11. So I didn't understand the first 10 minutes of the very first class in, my next math class. So I had to take 5 solid days at the library with multiple calculus books out, basically immersing myself in this material. And I think as a result of that, I have a unique perspective on it. And I really learned the material inside and out. So keep that in mind as we go through our journey into sequences and then eventually series. So here, let's get started by saying informally, you can think of a sequence as simply being an ordered arrangement of numbers. And that informally just means that there's a first member, a second member, a third member, etc. There's an ordering to it. But, we quickly need to get under control what a formal definition of a sequence is. So here's my formal definition of a sequence. A sequence denoted, and for a while I'll use the set notation and put the A sub n inside set notation. But here quickly I'll just stop leaving off the set notation. But a sequence denoted, the set A sub n, is a function whose domain is the set of positive integers. The functional values, so the a sub 1, a sub 2, a sub 3, and then those 3 dots, I tend to just call them, yada, 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 a sub n, yada, yada, yada. Well, those are called the terms of the sequence. So first things first, we're talking about a sequence being a function. The domain is the set of positive integers. So not reals, just positive integers. The functional values, or the range, if you will, they're called terms of the sequence, but they're exactly the same concept as being the range. And then one big note, A sub n, we're going to call the nth term of the sequence. So let me take a moment to also say a difference between me and your book. I think your book likes using K for some reason. instead of n. Most of the books out there, I mean, the vast majority will use n's. So as we go through this chapter and the next, your book and homework problems will be using the variable k. I'm using the variable n. That will really become apparent in the next section. But I thought I'd give you the heads up now. So hey, let's do an example. This first example is just simply listing the first 5 terms of a sequence. And I have 3 parts here. So in part A, the sequence A sub n is 1 over n. Part B, the sequence B sub n is 1 over 2n. And part C, the sequence C sub n is negative 1 to the n. So what I'm going to do, I'm going to head off to the chalkboard to do this example. You should make sure you write down this example, just as if you were in class. Actually, as you go through these videos, you should be taking notes, just as if you were in class. So I'm going to head off to the chalkboard and work out this example. All right, folks, here is that example. We are asked to list the first 5 terms of the given sequence. So in part A, the sequence we were given is A sub n equals 1 over n. So remember, the domain for a sequence is positive integers. So when n is 1, put 1 in for the n, you get the first term to be 1. The next domain element would be 2. So when n is 2, put 2 in for the n, you get 1/2. The next one is 3. 1/3, then 4, 1/4, then 5, 1/5. So keep in mind, this is as a result of when n is 1. This term is the result when n is 2. This term is the result when n is 3. This is when n is 4. That is when n is 5. So that would be the first 5 terms of that sequence. And I'm going to foreshadow, you're going to hear this in a little bit, coming up real soon. This sequence the sequence actually has a name. It's called the harmonic sequence. That's a sequence I would like you to know. I'd like you to know it by its name. It is the harmonic sequence. All right, moving on. Part B. The sequence was B sub n equals 1 over 2 to the n. So again, the first 5 terms, domain is positive integers. So we're looking at n values of 1, 2, 3, 4, and 5. So when 1 comes in here for n, you get the first term of the sequence to be 1/2. Then when 2 goes in for the n, you get the second term to be 1/4. When 3 goes in for the n, you get the third term to be 1/8. 4 gives you a 1/16, and 5 gives you 1 over 32. So those would be the first 5 terms of that sequence. All right, let's move to C. The sequence is given by C sub n equals the quantity negative 1 to the n. Same concept. Domain, positive integers. So we're looking at n values of 1, 2, 3, 4, and 5. So when 1 goes in for n, well, negative 1 to the first power is negative 1. When 2 goes in for the n, well, negative 1 squared is 1. When 3 goes in, you get a negative 1. 4 gives you a 1. 5 gives you a negative 1. So those would be the first 5 terms. Okay, so a couple of comments before I head back to the slides. Kind of foreshadow a little bit. It looks like the terms of this sequence, and it looks like the terms of this sequence. As we write down more and more terms, it looks like those terms are getting smaller. In fact, it looks like the terms are approaching the number 0. And we're going to talk about that in a little bit, how that correlates to an old word we know, the words converge, and how there's a limit concept embedded here. this sequence, it doesn't look like the terms are heading towards a single number. I mean, the terms are bouncing back and forth between -1 and 1, -1 and 1, -1 and 1. This one isn't heading to a number, so it's not going to converge. And if it doesn't converge, we tend to say it diverges. Some old vocabulary words. Also, another point that I'd like to mention real quick, -1 to the n, well, that's how we generate like what looks like alternating signs. The same would be true if that exponent instead of n, if it were n minus 1 or n plus 1. I mean, you might have them in a different order. They might go 1, -1, 1, -1, 1, -1, etc. But -1 to the n, or -1 to the n plus 1, or -1 to the n minus 1 is how you would generate these. All right, let's head back to the slides and see what the next topic is. All right, folks. Our focus for the present time is going to be dealing with sequences whose terms approach a limiting value. Such sequences are said to converge. So for example, the last example I did in parts A and B, it looked like in parts A and B from the last example, it looked like if we kept listing terms, those terms seemed to be approaching a limiting value of 0. So it appears that those sequences would converge to 0. Now when we say converge, it means the values of the sequence, they're getting close to a limiting value L. They're going to remain close to the limiting value L, and they're going to be arbitrarily close to the limiting value L. So what exactly does this mean? Well, let's head off to the chalkboard. I'll draw a picture there, and we'll see exactly what this means. All right, we left off on the slide with the following bullet point. It said, to converge means the values of the sequence get close to a limiting value L, remain close to the limiting value L, and be arbitrarily close to L. And I said, what exactly does this mean? Well, here's what it means. Trying to give an idea of what it means. First off, this break in my horizontal axis means, I don't know how many numbers are in there. I could go up to 5 billion. I just want to be larger than whatever, 5 billion, let's say. Notice that my horizontal axis is labeled with n, because we're dealing with a function of positive integers. And my vertical axis, I can call it y, but it's a sub n. So here's what's happening. Of course we have epsilon playing the game here. That when we see that arbitrarily close to the limiting value L, we should be thinking way back in Calc 1, we have to have an epsilon play the game. So let's say for small values of n, like n is 1, maybe if n is 1, I'm up here. I don't know what that number is, 5, say 5, it doesn't matter, it's irrelevant. Maybe when n is 2, it's here. Maybe when n is 3, the term, it's right here. Maybe when n is 4, it's here. It doesn't matter at the beginning, it's just that once I get beyond this value of m, once I get n values that are larger than m, the terms are going to be trapped between these two dashed, I don't know if you can see it or not, but I dashed them in red. They're going to be trapped between L plus epsilon and L minus epsilon. So that's what it means that the terms are getting close to this limiting value L. And they're going to be arbitrarily close to L, and they're going to remain close to L. So a note that I would make here, I'll give it a 1-star comment. that for any n that is greater than m, so for any positive integer that's greater than this number, for all of them, all of the terms of the sequence are trapped between L minus epsilon and L plus epsilon. So once I get to the right of this value, I'm greater than m, all of the terms are going to be trapped in here, trapped between those two horizontal red dashed lines. That's what that means. Now I need to formalize this. So I'm going to come over here to the right side of the board, and I'm going to write down a definition. So it's kind of formalizing this picture and what we said on the last slide. So we're going to say that the limit of a sequence a sub n, that limit is L. And we can write it as the limit as n goes to infinity of a sub n equals L. So we can write it like that. If for all, here we go, epsilon greater than 0, there exists a value m greater than 0 such that the absolute value of a sub n minus L is less than epsilon whenever, or I'll just say when, n is greater than uppercase M. These type of sequences let me say sequences with a finite limit. So we end up with an actual number. We're going to say those sequences converge, and then sequences that don't have a limit we're going to say those sequences diverge. Okay, so that's the hardcore definition. We're not going to prove anything like we did back in Calc 1, but I just wanted to give the picture, what it really means, and what the definition is. So what's kind of embedded in all of this, you know, it doesn't really matter what's going on for the first few terms of a sequence. And first few terms, that could mean the first 3 terms or the first 3 million terms. Those are the first few terms. When we're talking about going to infinity, 3 or 3 million, those are both considered few. It's what's happening in the long run. Once you get past a certain point, what is happening? What's the behavior? So, picture, there's the definition, and you know, I think right now what I'd like to do is a quick example. So let me erase the board, and we'll look at a quick example. Let me erase all this as well. So here's the example. let's find the limit as n goes to infinity of a sub n, where a sub n is the harmonic sequence, 1 over n. So something that we talked about a couple of weeks ago. And, you know, I'll write it down as another question here. What is the difference between a sub n equals 1 over n and f of x equals 1 over x? And no, it's not just simply, it's a difference of a variable. No, because that variable is really important. Using an n, we're talking about a function of positive integers. In fact, I could write this using function notation. F of n equals 1 over n. A sub n, it's a function of the positive integers. You know, here, f of x equals 1 over x, that's a function of the reals. So a function of the reals. So, you know, a sub n, the domain is positive integers. For f of x equals 1 over x, the domain would be all reals, as long as we exclude 0. Yeah, we are in Ohio. Remember, the graph of this would be discrete. It would just be dots. The graph of this is continuous. You know, it's a curve. It's a curve that would run through all of these dots. So because of that, and because we know that the limit as x goes to infinity of 1 over x, we know that limit is 0, we can conclude, and we'll formalize this here in a couple of minutes in a theorem. We can conclude the limit as n goes to infinity of 1 over n, it too is 0. Let me write that down here. The limit as x goes to infinity of 1 over x is 0. So what we're going to formalize here in a couple of minutes is, because we know what's happening with the real variable case, we can use that information to tell us what's happening for the positive integers. As long as these two functions are identical for the positive integers, and they are, the behavior of the sequence, it has to have the same behavior as the function of the reals. It's along for the ride. So this discussion is to set up something really important that I'm gonna get to here in a couple of minutes. But we should have known what this limit was without any of this analysis. You're looking at 1 over n. As n keeps getting larger and larger, you know, 2, 5, 500, 25 million, you know, positive integers keep getting larger and larger. 1 divided by ever larger numbers is going to be 0. But this is kind of foreshadowing what we're going to do next. So let's head back to the slides and see what this is all about. All right, hey, you may have seen something in the last example that looked familiar. If you remember, you know, a couple of weeks ago, we kind of explored this concept in class, the difference between a function of positive integers versus a function of the real variable, and how the graphs were different. That if you have a function of positive integers, the graph was said to be discrete. It was just dots plotted. Function of reals, it's continuous. The graph is said to be continuous, and the dots are connected. So as we saw in the last example, hopefully that was looking familiar. But if you have a sequence a sub n that agrees with the function of the reals, f of x, and they agree at the positive integers. Remember, agree means they're kicking out the same range values. And if the function of the reals, if it's approaching L as x is approaching infinity, then the sequence must converge to the same limit. See, we have all these wonderful tools on how we can do the limit as x approaches infinity of a function of x. I mean, sometimes we have to take it to the hospital. So if the sequence agrees with the function of the reals for all the positive integers, it has to be exhibiting the exact same behavior. It's kind of like it's along for the ride. And what we need to do now, though, is we need to formalize this whole idea in a theorem. So here's the theorem. Let f be a function of real variables such that the limit as x approaches infinity, f of x equals L. If the sequence a sub n, if it is a sequence such that f of n equals a sub n for the positive integers n, then you must have the limit as n approaches infinity of a sub n equals L. So when we say f of n equals a sub n for the positive integers n, that's saying that the sequence is exactly the same as the function of x for the positive integers. To say the limit as n approaches infinity of a sub n equals L, that's saying, hey, if the function of the reals, f of x, if the limit as x approaches infinity of f of x is L, then the limit as n approaches infinity of a sub n must also be L. If they agree for the positive integers, the sequence has the exact same behavior as the function of the reals. So, well, check this out. Here's something that we know from, Calc 1, and I think we've seen it this semester as well. The limit as x approaches infinity of 1 plus 1 over x to the x power is e. We know that limit. It's a function of the reals. That tells us the sequence, whose nth term is a sub n equals 1 plus 1 over n to the nth power. It has to have the same limit. It has to have the limit of e, because the sequence and the function of the reals, they are identical for the positive integers. So since we know the limit for the real variable case, we know the limit for the sequence case. Well, here's a quick comment. All those familiar limit theorems that you learned in Calculus 1, they're all true for sequences. So you could look in the book on page 650, Theorem 10.2. It just shows some of the limit theorems, and you should look at them and say, oh yeah, I remember those from Calc 1. But hey, let's head off to the chalkboard to do some examples. I don't know, I think I'll probably have 3 examples, and then I might have a few problems that I want you to do. So here we go, heading off to the chalkboard. All right, in this example, we are going to determine if the given sequence converges or diverges. And if it does converge, we're going to say what the limit is. So, at the beginning of it might not be a bad idea to list some of the first few terms of the sequence, like maybe the first 4 or 5 terms, to kind of have an idea of what's happening. It's really kind of important for the first sequence here, A, to list some of the terms. And here's like a little tip for me that I see here. When I see this -1 to the n, I know for the different values of n, the different values of the positive integer, -1 to the n is either +1 or -1, +1 or -1. So that tells me something may be happening here that I want to list some of the terms. So here we go. If n is 1, well, this would be -1, so 5 plus -1 is 4. If n is 2, well, -1 squared is 1. 5 plus 1, 6. If n is 3, well, -1 cubed is -1. 5 plus -1 is 4. If n is 4, -1 to the 4th is 1. 5 plus 1 is 6. I'm detecting a pattern here. I'm detecting that if I keep listing terms of the sequence here, it's going to go 4, 6, 4, 6, 4, 6, 4, 6, 4, 6, yada, yada, yada. This doesn't converge. This oscillates. It's an oscillator. It's bouncing back and forth between 4, 6, 4, 6. It's not approaching a single limiting value. It's not approaching a single number. This oscillates between two values. That means it diverges. All right, B sub n, again, you could list some of the first few terms. I'm not going to. I'm going to get down to the process of trying to determine the limit. Because if this limit exists and it's a finite number, then we know the sequence converges and we know what its limit is. So when I look at something like this, I immediately think of a very quick, easy algebra step to do. And that is, I look for the highest degree in the numerator and denominator. Well, the degree of the numerator is 1, the denominator is 1. Whatever the highest degree is, I'm going to divide by n to that highest degree. Well, since it's 1, I'm just going to divide everything in the numerator by n, and I'm going to divide everything in the denominator by n. So that gives me the limit as n goes to infinity. Well, n divided by n is 1. 1 divided by n, well, that's 1 over n. 3n divided by n is 3. Now remember, all of our old familiar limit theorems are still true. I'm not going to write them all out. I'm going to verbalize them. The limit as n goes to infinity of 1. Well, the limit of a constant is that constant. The limit as n goes to infinity of 1 over n. Well, that's 0. The limit as n goes to infinity, well, that's a constant. 1 over 0 minus 3 is negative 1/3. So the limit is negative 1/3. So our sequence, we say our sequence converges. The sequence converges, and it has a limit of negative 1/3. All right, moving on to C. Sequence a sub n equals n squared over e to the n minus 1. I could start off listing some of the first few terms. I don't think it's going to really help me because I have that e in there. I don't have a really slick, neat algebra trick for part C like I showed you here in part B. But what if we look at the function of x, which is x squared over e to the x minus 1. It's a function of the real variables. Is this function of reals and this function of positive integers, are they exactly the same for the positive integers? In other words, if you just toss positive integers in here for x, like 2, 7, 8, do you get the same thing if you just toss 2, 7, or 8 into the sequence? And the answer is yes. Because of that, we know whatever the behavior of this function is, the sequence is doing the exact same thing. It's along for the ride. So why don't we look at the limit as x goes to infinity of x squared over e to the x minus 1? That looks kind of familiar to me. It looks like it has the form infinity over infinity. So when I hear infinity over infinity, I immediately think, let's go to the hospital. So here we are, going to take this to the hospital. Alright, so we went to the hospital, and we still have the form infinity over infinity. Well, I guess we better go back to the hospital. Now the limit as x goes to infinity of 2 over e to the x. Well, that's 2 over an incredibly large number. That's 0. Because the limit we found for the real variable function, because that limit is 0, we can quickly conclude, so since this limit is 0, we quickly conclude that the limit as n goes to infinity of n squared over e to the n minus 1 is also 0. Folks, this is the one thing I'm really, really picky about. If you try to use the hospital rule in doing this limit here, so you have this and you write equals L, the hospital rule, limit as n goes to infinity, 2n over e to the n, I don't like that. I'm going to mark it wrong. You can't take a function of positive integers to the hospital. You can't do calculus on a function of positive integers. It's not a continuous graph. It's not a continuous case. You can only do the calculus on the function of the reals. We're using our knowledge that we know calculus. We can do that for function of reals. And the fact that these two functions are identical for the positive integers. So whatever the behavior is for the function of the reals, the sequence is along for the ride. We're using that fact to conclude that this limit is 0. So there's an example, and I actually have a few problems I'd like you to try right now. So go into the book. This will be section 10.2. In section 10.2, right now, I would like you to try 15, number 31, and number 61. So here's what I want you to do. I want you to pause the video. I want you to do these three. Once you have done these three, restart the video, and I'll be here at the board, and I'll work through the solution for each one of them. So pause the video, go to the book, section 10.2, do these three, and when you're done, restart the video. We'll see that you hopefully got them correct. All right, hey, number 15, you're given a sub n equals 3n cubed minus 1 over 2n cubed plus 1. So we need to look at the limit as n goes to infinity. 3n cubed plus 1, 3n cubed minus 1 over 2n cubed plus 1. I think I have an algebra trick here. The degree of the numerator is 3, degree of the denominator is 3, the largest, well, they're both 3. So I'm going to divide everything in the numerator and denominator by n cubed. So that gives me the limit as n goes to infinity. Well, 3n cubed divided by n cubed is 3. 1 divided by n cubed is 1 over n cubed. The denominator, 2n cubed divided by n cubed, well, that's 2. And then 1 divided by n cubed is 1 over n cubed. Now I'm going to use those old familiar limit properties. The limit as n goes to infinity of 3. Well, that's 3. The limit as n goes to infinity of 1 over n cubed. That's 0. The limit as n goes to infinity of 2. That's 2. And the limit as n goes to infinity of 1 over n cubed, again, that's 0. 3 minus 0 over 2 plus 0. The limit is 3 halves. So this sequence converges, and its limit is 3 halves. All right, 31. Let's see here. The limit as n goes to infinity of 3 to the n plus 1 plus 3 over 3 to the n. You know, the first thing I see a lot of 3's cruising around here, so I'm wondering if I don't take advantage of the fact that 3 to the n could be considered a common denominator, and just write this as 3 to the n plus 1 over 3 to the n plus 3 over 3 to the n. And then there's an old property of exponents. When the bases are the same and you're dividing, subtract the exponents. So 3 to the n plus 1 divided by 3 to the n, that would be 3 to the n plus 1 minus n. I subtract n plus 1 minus n. That gives me, well, just 3. And I'm going to leave this alone because I think now I can use old familiar limit properties to get the limit. I mean, the limit as n goes to infinity of 3. That's 3. The limit as n goes to infinity of 3. Well, that's 3. Oh, wait. Limit as n goes to infinity of 3 over 3 to the n. Well, that denominator is getting incredibly large. So the limit as n goes to infinity of 3 over 3 to the n, heck, that's just a 0. So the limit is 3. So this sequence converges, and it has a limit of 3. Let's see what's happening here in 61. So trying to do the limit as n goes to infinity, e to the negative n cosine n. Yeah. You know what, I'm going to start off by rewriting this as the limit as n goes to infinity of cosine n over e to the n. And I don't think it's going to help to turn this into a function of x. Even though the two functions, f of x equals cosine x over e to the x, and f of n equals cosine n over e to the n, they'd be exactly the same for the positive integers. And the point of taking it to a function of x would mean, am I thinking about going to the hospital? And I don't think that's going to help me, because think about the derivative of cosine x. Derivative of cosine x is negative sine x. And then the derivative of negative sine. You see how we're going to keep bouncing back and forth between cosines and sines, and the denominator is always going to be an e to the x. So I think I need to remember something else. Something we maybe haven't seen in a while. Something that if you suffered through Calculus 1 with me, I said this is a really important theorem. It's just going to keep popping up through the calc sequence. That's it. It's the squeeze theorem. I mean, look at what we have here. We have a cosine n. We know cosine n is trapped between negative 1 and 1. Let me write that down. That's what it means. We know cosine n is trapped between negative 1 and 1. Well, I can look at that compound inequality and I can say, hey, I'm going to divide each piece by e to the n. Now we know the limit as n goes to infinity of negative 1 over e to the n. We know that limit is 0. We know the limit as n goes to infinity of 1 over e to the n is 0. So thanks to the squeeze theorem, we know, so this is thanks to the squeeze theorem, we know the limit as n goes to infinity of cosine n over e to the n is 0. So this sequence converges, and it has a limit of 0. So hopefully you got those three. Hopefully you see, once again, here comes the squeeze theorem. But while we're here, there's one more thing I do want to put on the board and discuss. It's some special notation that we're going to start to see, in our study of sequences and especially series. And it's the old factorial notation. So it looks like this. That's an exclamation mark. I mean, it's read in factorial. Don't read it as n. It's read as n factorial. What it means, it's representing a product. And n factorial means n times n minus 1 times n minus 2 times yada yada yada. 3 times 2 times 1. So for example, 5 factorial. 5 factorial means 5 times 4 times 3 times 2 times 1. So that's what factorial means. Just want to practice something here real quick. So I'll call it, look at this. Before we do the look at this, that's what n factorial is. What would n plus 1 factorial, what would that look like? Well, it's a product still. It means n plus 1 times, 1 less, n times n minus 1 times n minus 2 times yada yada yada, 3 times 2 times 1. Or some people would say n plus 1 factorial simply means n plus 1 times n factorial, because that is n factorial. So what if we did the following? So here's ours. Look at this. What if I said, let's simplify n factorial over n plus 1 factorial? What would that simplify to? Well, we know n factorial is this. We know n plus 1 factorial is this, or you could write it like that. Do you see that if you had n factorial over n plus 1 times n factorial, the n factorials would cancel out, and that leaves you with just 1 over n plus 1? Hopefully you see that. If I said simplify n plus 1 factorial over n factorial, well, the numerator here is n plus 1 times n factorial. The n factorials would cancel out, and that would leave you with just m plus 1. So I wanted to do this simplification so we could try to figure out one really weird thing about factorial, and it is 0 factorial. What is 0 factorial? Now, a lot of people will say 0 factorial equals a number, and they'll say it's by definition. It really isn't by definition. It's because of either one of these two properties we just did right here, these two simplifications right here. If you want to figure out what n factorial, or what 0 factorial is, you could just put a 0 in for the n's. You'd have 0 factorial over 0 plus 1 factorial equals 1 over 0 plus 1. I'll write that down. But then is 0. So I'm using this. We have 0 factorial over 0 plus 1 factorial equals 1 over 0 plus 1. So that gives us 0 factorial. We know 0 plus 1 is 1. Well, 1 factorial, that's just 1. Over here on the right side you get 1. Anything in the world divided by 1, we know that just ends up being 0 factorial. So hey, look folks, 0 factorial is 1. I know many people in the math community that will say, by definition, 0 factorial is equal to 1. Well, really, it's by the definition of n factorial. There's a reasoning behind why 0 factorial equals 1. And I've just shown you, so hopefully this makes sense. But we're going to start to see this factorial notation going forward. Thought I'd point it out to you real quickly here. But hey, let's head back to the slides and see what's next. Next up is the absolute value theorem. This is a pretty powerful, important theorem. So here's what the absolute value theorem says. If you have a sequence a sub n, if the limit as n goes to infinity of the absolute value of a sub n equals 0, then the limit as n goes to infinity of a sub n also equals 0. So really it's saying, when we have the limit as n goes to infinity, absolute value of n, it's saying if you take the absolute value of each term of the sequence, and those terms are heading off to 0, then the limit as n goes to infinity of a sub n is equal to 0. So again, this is a pretty important and powerful theorem. And to show how to use it, I'm going to head back to the chalkboard, and we're going to see how the harmonic sequence and the alternating harmonic sequence are analyzed. These are going to be two sequences that I'm going to want you to know by name and know their behavior as well. It's going to be very important going forward through Chapter 10 and Chapter 11. So let's head off to the chalkboard to see what these two sequences look like and to see the power of the absolute value theorem. All right, we've just talked about the absolute value theorem, and I said it's a pretty important and powerful theorem. And let's see how we can use it to analyze what's called the alternating harmonic sequence. So first off, the harmonic sequence, I've already foreshadowed it. Here's the harmonic sequence, a sub n equals 1 over n. And I've listed the first 5 terms. It's 1, 1/2, 1/3, 1/4, 1/5, yada, yada, yada. The alternating harmonic sequence, which I wrote down as a sub n equals -1 to the n over n. The first 5 terms would be -1, 1/2, -1/3, 1/4, -1/5, yada, yada, yada. Notice the terms are alternating in sign. They're going negative, positive, negative, positive, negative, positive, negative, positive, yada, yada, yada. I could have written the alternating harmonic sequence as -1 to the n plus 1 over n. And if I did that, the terms would go 1, -1/2, 1/3, negative. I mean, it doesn't matter. That exponent could be an n plus 1, or an n minus 1. What I want to analyze right now is, does the alternating harmonic sequence, does it converge? And if it does converge, what is its limit? Well, we already know the harmonic sequence converges. We know the limit as n goes to infinity of 1 over n is 0. So the harmonic sequence converges using the power of the absolute value theorem. What the absolute value theorem says, it says, hey, if you take the absolute value of each term, so if you take the absolute value of each term, the negative terms would become positive. Notice if you take the absolute value of each term, you have the harmonic sequence. So the absolute value theorem says, if the limit as n goes to infinity of absolute value of n is 0. So if you take the absolute value of each term and that limit is 0, then the limit as n goes to infinity of the original sequence must be 0. Well, if we take the absolute value of each term here, we have the harmonic. I mean, the absolute value for this right here, the absolute value of every term is going to give you the harmonic sequence. And since we know the limit as n goes to infinity of the harmonic sequence is 0, we conclude, thanks to the absolute value theorem, we conclude that the limit as n goes to infinity of the alternating harmonic sequence is 0. So that's the power of the absolute value theorem. This is going to come up a little later on in this chapter, the concept of absolute values, and when we start to talk about absolute convergence. So it's nice that it came out early in the chapter. But let's head back to the slides and see what's next. All right, folks, as we continue our study of sequences, and here very soon when we look at infinite series, the ability to look at terms, if you're given the terms of a sequence, and detect a pattern, and be able to write down a general formula, like an a sub n, that's going to be kind of important. So for example, if you have the following sequence, 1/2, 1/4, 1/8, 1/16, yada, 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 we need to have the ability to recognize there's a pattern there. And we need to be able to recognize that this sequence can be represented by a sub n equals 1 over 2 to the n. Or another way to write that is a sub n equals the quantity 1/2 to the n. I'm using a property of exponents there. So it doesn't matter. You can rewrite it. You can write it as 1 over 2 to the n, or as the quantity 1/2 to the n. So the ability to recognize this is going to be pretty important. So let's try an example. I want you to write a formula for the nth term for the sequence given by 1/2, -1/4, 1/8, -1/16, yada, yada, yada. In fact, why don't you pause the video and see if you can come up with the formula for the nth term. And once you think you have it, restart the video, and I'll be at the chalkboard working out this example. Okay, I just briefly discussed that going forward, we're going to have the ability to recognize patterns. I mean, it's a small piece going forward, but it just keeps popping up that I thought it was worth the time now to briefly introduce it rather than hit you with it, later on. So I asked you to come up with the formula for the nth term, where you were given these terms of the sequence: 1/2, -1/4, 1/8, -1/16, yada, yada, yada. So hopefully you got it. Here's how I look at it. Oh yeah, well, 1/2 is 1/2. This denominator here, I see that's 2 squared. 8 is 2 cubed. 16 is 2 to the 4th. And since we're talking about a function of positive integers, this is n is 1, this is n is 2, n is 3. So these terms are for when n is 1, these terms n is 2, those terms n is 3, those terms n is 4. I'm seeing at least the denominator is a 2 to the n. All right, now I notice there's alternating signs. 1, -1, 1, -1, 1, -1, etc. So somewhere in here I got to have a -1 to some power. And it does matter what power I put down. For example, let's say I just put down it's -1 to the n. Well, if you list the first 4 terms of -1 to the n over 2 to the n, the first term is -1/2. The second term is 1/4. The third term is -1/2. The fourth term is 1/16. We don't have the correct signs. So I need to make this exponent something different than 1. I just kind of need to shift everything 1 unit and say the exponent is n plus 1. So you can check this. If n is 1, this exponent will be 2. Negative 1 squared is 1. So that would give us a 1/2. If n is 2, this exponent's a 3. Negative 1 to the third is negative 1. So we'd have negative 1 over 2 squared. So this is the formula for the general, what I call the nth term. So that was a quick look at looking at a pattern and being able to come up with a quick little expression for it. This will come up later on. So something to keep in mind, or I'm going to leave you with this little thought. For positive integers, what does the expression 2n plus 1 generate? What does the expression 2n generate? Let's head back to the slides. All right, hopefully you got the example there. And what we have coming up right now is the definition of a monotonic sequence. So folks, a sequence is said to be monotonic. That's not a new word for us. It's if its terms are non-decreasing, and that would look like this. A sub 1 less than or equal to a sub 2, less than or equal to a sub 3, less than or equal to yada, yada, yada. Don't know how many terms to write in there. Less than or equal to a sub n, less than or equal to, yada, yada, yada. That's what it means to be non-decreasing. Or if its terms are non-increasing, and that would look like this. A sub 1 less than or equal to a sub 2, less than or equal to a sub 3, less than or equal to yada, yada, yada. These are all greater than or equal to's. So a sub 1 is greater than or equal to a sub 2, which is greater than or equal to a sub 3, which is greater than or equal to yada, 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 greater than or equal to a sub n, greater than or equal to yada, yada, yada. So that's what it means for something to be monotonic. You're non-decreasing or you're non-increasing. So let's look at an example here on how we can determine if we have something that is monotonic. So 2 parts here. First is b sub n is the sequence given by 4 plus the quantity negative 1 to the n. And part B, the sequence is given by a sub n equals 3n over 2 plus n. So what I'm going to do is, you should write these down. Make sure you have them written down, because I'm going to head off to the chalkboard to work through this example. All right, folks, we've just seen a definition of what it means for a sequence to be monotonic. Hopefully that wasn't too surprising. And see, this example was to determine if the following were monotonic. So let's look at the first one. B sub n equals 4 plus negative 1 to the n. So if I start to list the terms of that sequence, when n is 1, the term would be 3. When n is 2, it's 5. When n is 3, 3. When n is 4, 5. It looks like I'm detecting a pattern here. The terms are going to go 3, 5, 3, 5, 3, 5, 3, 5. It's an oscillator. It's oscillating between 2 specific values. Is that monotonic? Absolutely not. This is not monotonic. So is this sequence monotonic? No. Okay, for B, the sequence a sub n is 3n over 2 plus n. And I went ahead and took the liberty and I wrote down the first 4 terms of the sequence. And when I look at the first 4 terms, I'm tending to believe it is monotonic. I mean, this one was obvious. It's not. It looks like the terms are getting a little larger. So it looks like it might be a monotonic increasing. So here's what we have to do to really show that it is monotonic. We must show, since each term is getting bigger, we must show that the n plus first term is a little larger than the nth term. This is the second term. That's the third term. A sub 2, A sub 3 when n has a value of 2 here. That's what we have to show. So here's where it's important for us to remember A sub n is a function of n. I wrote this down earlier. A sub n is a function of n. This is a function of n. Well, we know what A sub n is as a function of n. It's 3n over 2 plus n. And we have to show this is true. A sub n plus 1. It's just like evaluating a function. You're evaluating the function, f of n, you're evaluating it at n plus 1. So how do you evaluate a function at n plus 1? You put n plus 1 in for the n's. So you put n plus 1 in for the n. Well, let's see. I think what I would do next is not much. I just clean up this denominator to get an n plus 3. Okay, what I want to do now is I want to multiply both sides of this inequality by the LCD. We know what the LCD is. The LCD is a 2 plus n times an n plus 3. But I have to make a quick check of something. I remember back in algebra that when you have an inequality and you multiply both sides of an inequality, sometimes you have to flip the inequality sign. Remember, when you multiply both sides of an inequality by a negative number, you have to flip the inequality sign. So I need to do a quick check to make sure symbolically I have to make sure I'm not going to be multiplying both sides by a negative number. But keep in mind, n is representing a positive integer. For positive integers, 2 plus n will always be positive, and n plus 3 will always be positive. A positive times a positive is positive. I don't have to worry about, when I multiply both sides of this inequality by the LCD, I don't have to worry about possibly inadvertently multiplying by a negative. I know the product is positive. So here we go. Multiply both sides of the inequality by the LCD. We get a 3n times an n plus 3 is less than a 3 times an n plus 1 times a 2 plus n. Now if you go ahead and you multiply this out, you get a 3n squared plus a 9n. Over here, if you multiply all that out, you're going to get a 3n squared plus a 9n plus a 6. My next step would be to subtract 3n squared from both sides of the inequality and to subtract 9n from both sides of the inequality. That gives me 0 is less than 6. Well, hopefully we all believe 0 is less than 6. That is absolutely true. This is true. So here's what you would have to technically do. I'm happy with this, what I see here. But technically, if you're in a serious stickler, an absolute stickler, hardcore math type person, you would start off with this line right here. You would start off saying 0 is less than 6. No one's going to argue with that. Then you would write this line down. Then you would write this line down. Then this line. And then this line. And then this line. So you'd have to write everything in reverse. But I'm happy with this because I know if you can do this, you could write everything down in reverse. So what we have shown is this is true. This led us to a true statement. We have shown that a sub n is less than a sub n plus 1. We have shown that this beastie, all of this shows that this beastie is monotonic. So the big deal with the monotonic, knowing a sequence is monotonic. Think about this more if you're really going to go on and get a math degree or an advanced math degree. That if you know something is monotonic, one of two things is happening. It's either heading off to infinity or negative infinity, or if there is a bound, like this one's monotonically increasing, if there is a bound, what's called an upper bound, a ceiling if you will, and it's increasing, then it has a limit. Likewise, if you know it's monotonically decreasing and there's a floor, you would know there's a limit. That's all I'm going to say about that. But I do want to point out one more thing about part B. So let me erase this. I just want to keep part B up here. We know the answer. We know it's monotonic. We could have done the following. We could have said, well, let's look at f of x equals 3x over 2 plus x. Does the function of the real and the function of positive integers, are they identical? Are they exactly the same for the positive integers? The answer is yes. So whatever the function of the reals is doing, whatever its behavior is, this function is along for the ride. Well, let's see. We know the derivative of this function. So, if you crank this through the quotient rule, you're going to get the derivative, and I'm going to have the simplified derivative here, is 6 over 2 plus x quantity squared. Well, think about it. To determine if a function is increasing or decreasing, we use the derivative. The derivative tells us if a function is increasing or decreasing. Look at this derivative. For any real you can think of, and you put in here for x, the derivative will always be positive. If the derivative is always positive, that tells us the function is increasing. If my function of the reals is increasing, the sequence, it's along for the ride. That tells me a sub n, it too is monotonic. So that's just a way to show, to give you another way to look at it. I've talked about this a couple of times in this section, about how you can use your knowledge of the function of the reals to help you with what's happening with the sequence. But that's it. That's it for sections 10.1 and 10.2. So now you can do the homework in sections 10.1 and 10.2. And hopefully they don't treat you too badly. Thanks for watching.